Hello viewers, my name is William Cothra and I represent Team ME65. My project is on understanding the performance of magnetorheological fluids and smart dampers. My direct advisors and sponsors are Drs. Jiyoung Tang and Richard Christensen, and our sponsoring partner is the Office of Naval Research. Upon commencement of this presentation, it must be known that the investigation conducted herein constitutes the beginning of a 2-year research assessment in support of an MS thesis. Milestones such as testing, raw data acquisition, and hypothesis validation have yet to be concluded or may be classified as controlled information. The deliverables for this year's study were as follows: to perform an extensive literature reviews pertaining to the existing and ongoing research findings in relationship to smart damping technologies, establish mathematical models describing smart damping behaviors, and design of experimental testbed and validation for assessing the long-term durability and stability of magnetorheological fluids. So what are magnetorheological fluids? Well, MR fluids are generally composed of micron-sized ferrous particles which are suspended within a carrier fluid, such as mineral or silicone oil. And when this fluid comes in contact with a magnetic field, the fluid's viscosity changes almost instantaneously. This change in viscosity is directly proportional to the applied magnetic field intensity seen by the fluid. Unlike traditional passive damping technology, this principle gives way to the incorporation of automated predictive control pertaining to vibration suppression. The current technology is being used in industrial applications such as vehicle shock absorbers and structural base isolation systems, which may experience unwanted or unexpected amplitudes of vibration or shock. However, lack in ongoing research relating to long-term durability and stability of the MR fluids is yet to be conducted. Magnetorheological fluids are known to contain yield stress values in excess of 80 kilopascals. This is pretty exceptional considering the fact that the best electrorheological fluids used in industry today contain at most a yield stress of 3 kilopascals. MR fluids also have the capability to operate in a wide range of temperature, ranging from -40 to 150 degrees Celsius. The yield strength varies only slightly over this broad temperature range and is only due to a change in particles volume fraction due to expansion and contraction of the carrier fluid. As mentioned previously, the response time is another contributing factor which makes this fluid so appealing. MR fluids can respond to a magnetic field in milliseconds. Prototype MR dampers have been constructed, for example, and been built to reach rheological equilibrium in less than 6.5 milliseconds after being exposed to a magnetic field. Lastly, raw materials are non-toxic and safe for the environment. While this robust principle seems simple enough, modeling and control of MR dampers poses a challenge due to nonlinearity and time independency phenomena pertaining to the fluid's magnetic retentivity and coercivity. Here I provided a magnetic hysteresis loop to illustrate what I mean by retentivity and coercivity. Every material that comes in contact with a magnetic field will have different variations of hysteresis loops pertaining to its amplitude and width. The shaping of such loops depends on the material's overall magnetic permeability or the ability to absorb magnetic flux before becoming saturated. Generally, if a material contains a high value of permeability such as iron or cobalt, it will retain some of the flux density after the magnetic field has been removed. This can be seen as the path from A to B. Instead of a reversible process where the flux density returns to its origin of equilibrium immediately, some time is needed for the flux density to discharge before returning to the actual equilibrium. This part can be seen from the path B to C, and better intuitively understood as the displacement of C projected onto B or the origin. The process is then repeated in the opposing direction by applying a reverse magnetic field until saturation occurs. The cycle is then repeated, thus closing the loop. The force versus velocity curve seen to the left perfectly describes the response of an MR damper under a constant applied magnetic field, resulting from a voltage of 1.5 volts applied to an electromagnet. The damper actuation consisted of repeated amplitude and frequency of 1.5 centimeters and 2.5 hertz. This force versus velocity curve perfectly describes the hysteretic behavior as mentioned previously. One will note that the actuation never returns back to the origin as the damper continues to reciprocate throughout its actuation cycles. One will also note that as the velocity increases, the graph almost becomes linear. This indicates that the magnetorheological fluid has then saturated, and the only reason why force is thus increasing is because it's acting like a traditional passive damper where the force is strictly proportional to the fluid velocity. Additional to understanding the importance of the hysteretic behavior that takes place within an MR damper, it is also very important to be able to reproduce a manageable yet accurate mathematical model which then can be used as the system's plant for controller development. Here I take use of a modified Book-Wind model, which is commonly used to model hysteresis phenomenon in a wide range of engineering disciplines. The system is composed of a 2 degree of freedom mass spring damper system to illustrate the relationships between the independent and dependent variables within a linear MR damper. The model includes a Book-Wind device in parallel of both spring and dashpot, which is also in series with an additional damper. The Book-Wind mechanism is formulated and implemented to address the shape fitting of the hysteretic behavior that takes place during actuation. Here I have attempted to reproduce such phenomena and took use of the parameters shown previously. You'll find a Simulink model attached, as well as the observed behavior of the phenomenon seen from data acquisition and the simulated behavior reproduced from the Simulink model. The outcome of such model resulted in an overall error of 4.45% from the actual force versus velocity acquisition data. Speaking on behalf of the overall fluid durability and stability, one must consider the powder-like iron particles contained within an MR fluid. It is well known when such ferrous materials are exposed to any level of oxygen, the elements experience a trade-off of electrons, resulting in a chemical reaction known as oxidation redox. When oxidation occurs, a brittle layer of iron oxide forms on the particle's outer surface and is propagated when exposed to elevated temperatures. In the case of an MR fluid, when the fluid is exposed to high levels of interparticle stresses during constant operation, this less dense surface layer breaks into nano-sized particles, which contain a large surface-to-area ratio. As the process continues over time, the accumulation of these particles results in in-use thickening, which solely depends on the fluid shear rate, temperature, and duration of usage, thus increasing the overall viscosity of the fluid during its off state. The above data describes an MR fluid life cycle test using a Motion Master TM-RD truck seat damper. The damper was operated at 1 Hz with a 25.4 mm stroke in the on state with 1 amp applied continuously such that the damper force was approximately 1200 newtons. One can note that after 600,000 cycles, this fluid's viscosity during its off states nearly tripled. Since the Motion Master durability test, research has been invested into reformulating the chemical makeup of conventional MR fluids. The best MR fluids today can sustain approximately 10 megajoules per cubic centimeter before they have thickened to the point where they are no longer useful in controllable MR fluid devices. Translating this to the Motion Master test, it would take nearly 121 days of continuous loading to achieve in-use thickening similar to that of the original analysis. For this reason, I propose an experimental magnetorheological rotary damper, which will be used to assist in reducing the amount of time to exhaust the fluid life of modern MR fluids, while simultaneously being able to obtain MR fluid performance metrics, such as fluid permeability, change in viscosity, yield and overall shear stresses and rates, force dissipation or torque, thermal conductivity of the fluid, and the effects of elevated temperatures may have on the overall performance of the fluid. The proposed rotary MR damper consists of a servo motor, 2 couplers, a housed bearing and support, the MR rotary damper itself, and a reaction torque sensor. Additional to the components seen here, there will also be a thermocouple attached to the MR damper to measure any variations in temperature change during actuation. The rotary damper itself contains an aluminum bobbin, which will be housing the electromagnet. It also contains a mild steel rotor measuring in a diameter of 100 millimeters. The MR fluid will be housed within a gap measuring in 1 millimeter thickness, which will completely surround the rotor itself. The torque shaft itself is also made from mild steel and has an effective diameter of 22 millimeters. To keep the fluid contained within the MR working gap, Turcon Vari-Lip PDR rotary seals are being considered for implementation. Such design will allow for analysis pertaining to the fluid movement known as Couette flow, which can easily be analyzed from a one-dimensional perspective. Using Couette flow, the fluid will be operating under continuous pure strain conditions as the MR fluid is housed between a rotating rotor and a stationary housing. With this design, we can also evaluate the long-term durability of the MR fluid pertaining to its in-use thickening by periodically removing the applied magnetic field during operation and measuring the torque the base fluid applies to the rotor. As the in-use thickening begins, the base fluid will become more viscous, thus applying an increasing torque on the rotor. Once the base fluid reaches 80% of its original base torque value, we conclude the fluid has reached the end-of-life conditions. Assuming the fluid adheres to the no-slip boundary conditions of the rotor and stationary walls during operation, the following models are proposed to extract the performance metrics previously mentioned. The proposed torque models shown below here take into account both the no-slip boundary conditions as well as slip boundary conditions. From literary research, it has been shown that the no-slip boundary conditions holds true mainly for when the magnetorheological fluid is being exposed to a magnetic field. However, during the off state, it has been shown that sedimentation occurs on the outside or the outskirts of the control volume and must be taken into account when acquiring data. From literature view, I expect shear thinning of the fluid post-yield as the rotor approaches the steady state angular velocity from rest. This can be seen in the following empirical results. Here below, I've provided 3 separate transient torque analysis pertaining to torque versus angular velocity. Case A represents a magnetic fluid which sees a magnetic field with a value of 81,250 amperes per meter. The second is 356,250 amperes per meter, with case C being 493,750 amperes per meter. Case A represents more of a theoretical torque value with a steady state torque value of 10.2124 Newton meters. Case B and C are not realistic since MR fluids are known to have a flux density saturation value of roughly 300,000 amperes per meter. This can also be seen from the dynamic viscosity versus shear rate curves to the right. To validate these findings, I performed a finite element analysis using ANSYS Workbench. Within ANSYS Workbench, I also used the built-in function calculator to obtain the torque applied to the wall from the wall shear stresses seen by the MR fluid. The torque acquired from ANSYS resulted in 9.8055 Newton meters. This value of torque results in a 3.9% error difference as compared to the theoretical results obtained from the model shown previously. Such deviations could have been brought on due to meshing techniques, however, nevertheless, an accurate and acceptable validation. As previously mentioned before, this 2-year assessment is part of an ongoing research supporting an MS thesis. Thermal analysis pertaining to the fluid's transient thermal conductivity and performance are still being evaluated. The models below to be used constitute as a system of 2 coupled nonlinear differential equations and were derived from the Navier-Stokes, momentum, and energy equations. The system relates the fluid's nonlinear velocity profile to that of viscous shear heating of viscoelastic fluids. This concludes the presentation regarding the performance of and durability of MR fluids within smart dampers. Thank you very much for watching.